All right, today we're going to decode what is basically a secret language. It's this amazing concept that engineers use to connect two worlds that honestly seem like they have nothing to do with each other, and it helps them solve some of their absolute toughest problems.
So let's just kick things off with a question. Really think about this. What on earth could a massive skyscraper, designed to stay cool in the blazing summer heat, what could that possibly have in common with the tiny, super powerful processor humming away inside your smartphone? Well, the answer is kind of wild. At a really fundamental level, they're both designed and figured out using the exact same secret language. It's this incredible framework that lets engineers literally see the invisible world of heat in a completely new light.
Okay, let's get into it. This secret language has a name, of course. It's a super powerful tool called the thermal electric analogy. And listen, this is not just some clever metaphor. Nope. It is a really solid, rigorous method that has been a cornerstone of engineering for decades.
The core idea here is actually brilliantly simple. What it does is it translates the super complex and, let's be honest, often confusing physics of how heat moves around, and it turns it into the world of electrical circuits, which is something we understand really, really well. It's visual. By doing this, engineers can basically build a heat problem on paper, just like a circuit diagram, and then solve it using the rules they already know from basic electronics. It's a game changer.
So, how does this translation actually work? Well, to use the analogy, we first need a kind of dictionary, a way to map the key ideas from the thermal world over to the electrical world.
First up, you need a driving force. In electricity, that's voltage, right? A voltage difference is what pushes electrons to move through a wire. In the thermal world, the driving force is a temperature difference. Heat naturally flows from hot to cold. If there's no temperature difference, there's no heat flow. It's the exact same principle. So, what's actually flowing? In a circuit, it's the electrical current. That's the flow of charge, measured in amps. In our analogy, the thing that's flowing is heat, specifically the heat transfer rate. That's the flow of energy per second, which we measure in watts. So you can just think of watts of heat flowing exactly like you think of amps of current.
And this is basically the Rosetta Stone for the whole thing. Look at this. It lays it all out, side by side. We've got temperature difference acting just like voltage. Heat flow is our current, but it goes even deeper, right? Opposition to flow becomes thermal resistance, and the ability to store energy becomes thermal capacitance. Once you have this table, you can take pretty much any thermal problem and redraw it as a simple electrical circuit. It's that powerful.
Okay, now let's see how this actually builds into real-world stuff. How do we model the materials that block heat, like the insulation in your walls, or store it, like a big concrete slab?
So anything that gets in the way of heat flow is just a thermal resistor. The insulation in your attic, the ceramic case on a computer chip, they all have thermal resistance. And as the formula here shows, that resistance depends on how thick the material is and its thermal conductivity. So materials that are bad at conducting heat, like styrofoam, are just high-value resistors in our circuit diagram. Simple as that.
And here's a perfect simple example. A standard wall in a house is just a bunch of resistors in a series. Heat has to flow from the warm inside air, then through the drywall, then through the insulation, then through the brick, and finally to the colder outside air. Just like in a series circuit in electronics, we can just add up all those individual resistances to find the wall's total resistance and figure out how much heat we're losing.
But what happens when you stick a metal stud, like a steel one, right in the middle of that nice insulated wall? Suddenly, the heat has a choice. It has two paths it can take. It can struggle through the high-resistance insulation, or it can zip right through the superconductive steel stud. That's a parallel circuit. The steel stud basically acts like a short circuit for heat, creating this cold spot and pretty much ruining the whole point of the insulation. Engineers have a name for this. They call it a thermal bridge. Now for the other key component, storage. We call it thermal capacitance or sometimes thermal mass. It's just the ability of an object to store heat energy. Think of it like a thermal battery. Heavy, dense materials like concrete or water, they're like massive capacitors in our thermal circuit. They can soak up a ton of heat without their own temperature changing all that much.
And this ability to store heat has a really profound effect, especially in architecture. What it does is create a delay or a time lag in how a building responds to the temperature outside.
Just look at this timeline. It's a perfect example. The sun is absolutely blazing at, say, 2 p.m., just baking the outside of a heavy concrete building.
But all that heat energy has to charge up the thermal capacitor, the concrete wall itself. So by the time that wave of heat finally makes its way to the inside, it's 10 p.m. The hottest part of the day hits the inside of the building in the cool of the night when you can just open a window and let it all out. That's passive cooling, and it's all designed using a simple concept from electronics, an RC circuit.
Now, this is all great for buildings, but this analogy is just as critical, maybe even more so, in the world of high tech, where getting heat out is absolutely everything.
You see, in modern electronics, heat is the ultimate enemy. The speed of your computer isn't really limited by the silicon chip itself, it's limited by our ability to keep that chip from melting. And the thermoelectric analogy is the first and most essential tool that every engineer reaches for to tackle that problem.
So here's the obstacle course that heat has to run to escape a computer chip. It flows from the superhot silicon junction out to the chip's casing, then through some thermal paste to a big metal heatsink, and finally from the heatsink out to the air. Each one of those steps has a thermal resistance. So an engineer just adds up these three resistances, multiplies that by the chip's power in watts, and bam, they can instantly predict the final temperature of that chip.
So we've seen how it works, but it's really worth taking a step back and asking, why does it work so well? What's the secret that makes this analogy so powerful?
And here's the really deep part. This isn't just a convenient trick, The reason this whole analogy works so perfectly is that the fundamental physics, the math behind it all, is identical. The equation for heat conduction, Fourier's law, and the equation for electrical conduction, Ohm's law, they're basically the same equation. They're both describing what's called a diffusion process. So the universe literally uses the same math to describe how heat spreads out and how electrons flow. How cool is that?
And that, ultimately, is the power of a really great analogy. It lets us take a problem that's complex and invisible and reframe it as something familiar and solvable. It connects these totally different fields of knowledge and turns some pretty daunting physics into simple puzzles we already know how to solve.
And that really leaves us with a final thought, doesn't it? This whole thing works because of a deep, hidden symmetry in the laws of nature. And it just makes you wonder, what other invisible forces, what other incredibly complex systems out there are just waiting for someone to find the right analogy, to translate them into something simple, something we already get?